Oh, here we go. So let's see. You want to briefly not share your screen. Okay, I'm not sure who's the. Okay, anyways, maybe just a small figure in some box on your screen, but I'm Mike Douglas, and this is the CMSA New Technologies in Mathematics seminar. And today we're delighted to have François Charton from Meta AI, who will tell us about math for transformers and transformers for math, or maybe it was the other way around. But in any case, transformers are very versatile and multi-talented, and we'll learn some more of their talents in Francois's talk. And as I always do, I'll watch the chat. So if you have a question that you're not totally sure about asking, put it in the chat, and we can ask it or reply to it. And feel free to ask questions as we go, and then there'll be time for questions at the end. So without further ado, please, François.
Yeah, hi. So I'm François Charton. Can you hear me, people on Zoom? Does it work?
Yes,
yeah, okay, it seems so. Okay, so let me try and share my screen. This should be shared. Okay, there we go. So I'm François Charton, I work in Meta, and my talk is called Transformer for Math and Math for Transformers. So I'm starting first with Transformer for Math. What do I want to do? I'm interested in solving problems of mathematics and solving them by taking them as a translation task. You know, transformers were invented for translation, so why not do that? So practically, I want to generate sets of problems and solutions to mathematical problems, and I want to train my transformer to translate the problem, which is a mathematical sentence, into the solution, which is another mathematical sentence, just as if it were a translation from French into English or something. So to give you a few examples, I'd like to work with a sentence like 7 plus 9, 3 words, and translate it into 16, 1 word, or 2 words if you want to take it as digit as a word. Or I would like to have x squared minus x minus 1, 6 words, and translate it as the roots of the polynomials. So giving an example that we're going to see again, suppose I want to learn to compute the greatest common divisors of 2 integers, say 10 and 32, GCD is 2. I can represent 10, you know, as a sequence of digits, the way we write them, plus 1, 0, 32 as plus 3, 2. And so I want my model to learn to translate the long sentence, plus 1, 0, plus 3, 2, into plus 2. And I want this to happen just from examples, so the model will not know anything about mathematics. And as a pure language problem, you know, like if it were translating. And by the way, at this point, I have to add that, you know, the fact that the words are plus 1, 0, plus 3, 2 is totally irrelevant. It could be red, blue, yellow, banana, blue, red. It would work as well. The meaning of the word has absolutely no importance for the machine. So surprisingly, this works. You can do quite a bit of mathematics. So I've been doing that for about 4 years. A couple of years ago with Guillaume Lamp, we proved that you could use this technique to calculate, to integrate functions, to calculate symbolic integrals of functions or symbolic solution of ODE. And you could do this pretty much at the same level as Mathematica, so state of the art. With Amaury Ayat, we showed that you could find properties of dynamical systems, you know, like Kalman control things. I did linear algebra with that, compute eigenvalues. We used it to do transport graphs in computational biology. We used it for symbolic regression, and more recently, I used it to do cryptanalysis of post-quantum cryptography. And you can do all that, you know, just as translation tasks. So you might wonder why do that? You know, after all, we have lots of tools that do math. So first idea is that it's a challenge. It's like Go, it's like chess, you know, the kind of thing when people say, okay, when transformers can do that, they will be intelligent. Of course, it won't happen. But like Go, like chess, it will teach us a few things about AI and transformers. So it's an interesting line of research because of that. A more serious reason is that more and more people are interested in doing AI for science, solving problems of science doing AI. And science is full of math. So if you're transformer cannot do math, there's no chance it will do science ever. So it's important to do AI for math in order to do AI for science. And as I said, there are a couple of practical uses of that, one of which is cryptography. So at this point, you must see, all of my problem will look similar. I have three things I need to do every time I want to solve a problem. I need to represent my problems and my solution as sequences, because transformers process sequences of words. I will need to generate sets of problems and solution, and then I will need to train the models. Yeah.
Can I ask a question? So you're making a distinction between translation and sort of like a autoregressive decoder predicting the answer given a previous sequence where you can imagine this more
So
decoder setup.
So I'm using an encoder-decoder setup all through, because this is the model I used in the beginning. I could use encoder only, a la BERT, if I can guarantee that my output is shorter, my output sequence is shorter than my input sequence. And just an encoder and a decoder at the top, this would work. Decoder only would probably work, but the point of the decoder only, the autoregressive all over means that you're going to spend a lot of compute trying to predict the question. And in mathematics, trying to predict the next, like the next coefficient in a matrix is a thankless task. It's also a useless task. So I have the impression, I never tried it, that decoder-only models, they would perform, but they would be less efficient than the encoder-decoder.
I guess the thing that's confusing, maybe it's not a problem, is that I would normally think that some of the problems would be quite long. Like you might have, for the simple arithmetic questions, you have some long expressions that you want to simplify, and the answer maybe is just a single number. And whereas normally should I not think of translation as having like strings for roughly the same?
No. In translation, you can have translation of long to short, short to long, or long to long. And in some cases, I use the same model, when the output is just one token, and when the output is as long, and sometimes even longer. We'll see examples where actually the output is longer than the input. The only good thing with seq-to-seq is that you can have different length. So you don't have a constraint, of the output being shorter than the input or something like that. That's the only good thing. So, or representing everything as problem and solution as sequence is not really difficult. I'm talking to mathematicians, so I'm sure you understand that most mathematical objects are either symbols or sequences. So constants are symbols, vectors and matrices are basically sequences of numbers, graphs are sequences of edges, pairs of nodes, etc. So everything is already pretty much in sequential form. There are only two issues that you need to settle. How do you want to represent numbers? And how do you want to represent expressions like functions and all that? So for numbers, for integers, we've seen that integers, we write them as sequences of digits encoded in some base. So 1024, you can represent it as 5 tokens plus 1024. If you think it's too long, you take it in base 100 and it's plus 1024. You can always do that. Once you have the integers, you can do the rationals. You can do some of the real numbers by considering their symbol. Pi is a symbol, square root 3 is a symbol, or 2 symbols. So you could do that. But in practice, when we want to do approximate calculation, we just encode them as in computers. So real numbers are considered as base 10 floating point numbers. So they are a sine, a mantissa, an exponent that you can represent as single tokens or as sequence of numbers. They're basically digits, right? So this is easy. For expressions, it's an old trick, in computer science. You can always represent an expression as a tree, syntax tree, or they call it. So practically all the operators are the internal nodes of the trees. And the numbers or the letters and all that will be the leaves. And you see here 3 examples where you can do things more and more complicated just by increasing the vocabulary. And the good thing is that once you have a tree, it's very easy to enumerate a tree into a sequence. The best known way to do that is the Polish notation, from the Polish logicians from the 20s or 30s. Which is also known from computer scientists as pre-order enumeration. Start from the roots, enumerate parent before child, and then left children before right children. So here, start from the root, so plus, left parent 2, right parent, start from the root times 3 plus 5, 2, etc. So this way you could enumerate anything into sequences, and we're pretty much done with the first phase, which is you can represent a lot of mathematical problems this way. we're going to need to generate data. So everything is trained from generated data sets. And I'd like here to insist on the fact that there are basically two ideas. If you work on a problem you already know how to solve, then the natural way to generate data is relatively easy. You generate a random problem, and then you generate a solution. You calculate a solution with a tool you have, and then you have a pair, problem solution, rinse, repeat that 10 million times, and there you go. If you're working on a hard problem, on a problem you cannot solve, and an open problem, a problem you can solve only some instances, you need to find another way. And surprisingly, many problems are amenable to what we call the backward method, where you generate the solution and you try to find a problem. And you can go along with this way. We'll see the two during the presentation. Finally, you're going to train models. So the model is trained on generated data. You can see I have problems and solutions. So this is supervised learning. All of this is supervised. It's a language task, so we just minimize cross entropy. Practically, the model gets a reward every time it predicts correctly the next token, and it gets punished every time it doesn't. And it's a pure language task. So during training, you don't need to understand anything about the problem you're solving. The model is not caring about the problem, the mathematical problem it's solving. Of course, at test time, you're going to do mathematics. You're going to test on external data, not seen at training. And you need an external tool. So this is one strong limitation of this approach. You need to have a way to verify the prediction, that the prediction done by your model is correct or whether it is wrong. Okay? And this will always be a mathematical approach. So that was the introduction. So let me present you a couple of examples of this. So the first one is a paper from last year with Stéphane Descoli. Basically, we wanted to address a problem that you might know, IQ test. I'm giving you a sequence of digits, a sequence of numbers, and you're supposed to predict the next one. So I'm giving you 1, 2, 4, 7, 11, 16, and you're asked, okay, what's the next one? So there are two ways to do that. There's the statistical approach, the time series approach, where you have a model that have a lot of techniques, could be regression techniques, could be autoregressive moving average models. You look at the number very hard and you predict the next one. But what we humans tend to do is more something in the line of symbolic regression. We try to find a formula for the numbers, and we use this formula to predict the next one. And when you look for a formula, you can look for a closed formula or a recurrence relation. And I'm ready to bet that if you try to solve the problem in your head while I was talking, you probably found this recurrence relation, and you probably went for a recurrence relation. This is the way we are sort of built. So we're going to consider both numeric regression and symbolic regression with transformers, so two different cases. And we're going to look at two cases, integer sequences, which is IQ test, but also real sequences, because that's where it might become interesting in practice, if you want to do physics or anything with this. So you need to generate data. You see, obviously, we have to go the backward way. There's no solver for this. So we're going to generate a random function, okay, of variable of n and of the previous term, so a recurrence. So here I would generate, the function n plus un minus 1. Then sample a first point randomly, and then I use my function to calculate a long sequence from that. And I have two cases, symbolic regression, where I'm providing the model with the 5 or 6 or 10 first terms in the sequence, and I task it to predict me a sequence of token, which is the formula. And in the numeric case, I provide it with the first terms, but it starts to predict the next values. Right. How do you generate formulas? Remember, formulas are trees. So to generate a random formula, generate a random tree and just decorate it randomly with the elements I want. This works well. Of course, depending on whether your integer sequences or float sequences, the operators you use must be closed. So you're limited in the functions you can use with integers. You have the for operation, the modulus, the square, but that's pretty much all you have. Whereas if you go for floats, you can use the log, the exponentials, so you have a larger function space. Okay, and then finally, you want to evaluate performance. So this is where we do mathematics. There's no point here. We want to evaluate the next terms or the next terms in the sequence. There's no point trying to understand whether the formula found was the correct one. First, because there are several ones. because there are many equivalents. So we judge the model just by its performance. We make it predict, and we see whether it predicts correctly or badly. And here you need to have kind of a L infinite norm or something like that, because you want all the predictions to be correct. It's not good if you can predict the 3 first one and you're totally wrong on the 7 next. Okay, so this just to show that, you know, designing those generating and testing elements are where you do, mathematics. So results. The main results, so in the main results here, we're testing on function that the model hasn't seen at train time, but that were generated the same way that the training data was done. And you can see you have, you have the symbolic and the numeric models. So in the symbolic, I'm predicting a function. Numeric, I'm directly predicting the values for integer and full values. And you can see here that the symbolic model always outperformed the numeric prediction, which is good because it's exactly what we humans do. And it looks like the transformer does like that, but it's also very unintuitive. Because, you know, you would think that predicting a function from numbers is a much harder task than trying somehow to guess the next term. And it's not the case here. You can see that the float results are harder than the integer results. I said, you know, you have more functions in the problem space, so that's only normal. And there's the 2 columns are the number of operators, so small functions, big functions. So the larger the function, the more difficult it gets. But still, you can see you can predict a lot of those functions. Okay, so it sort of works. In that case, we had an ID when we started that, and the ID was the test set. There's something called the Online Encyclopedia of Integer Sequences, which is a huge database of all kinds of integer sequences. Not all of them mathematical. You've got the number of stops in the Brooklyn line subways as one of these sequences. And you have things that are absolutely not, you know, recurrences and all that. So you can have all kinds of things, but it was a good test set because it was something totally external. So what happens if you test there? You can see that the symbolic model, when predicting the next element, succeed in 1 case out of 3. So that's disappointing. We're far from the 92%, but still it's way above whatever chance level would be. The model still can manage that. Interestingly, the numeric model works better than the symbolic here. And the reason is that the model was trained on, you know, recurrent sequences. If you test it on non-recurrent sequences, the inductive biases that you've built into the training set doesn't hold anymore in the test sets. So somehow the model worked better. The model trained on recurrent sequences worked better for predicting recurrent sequences. But if it's not what you have at test time, then it becomes less good. Yeah. So we didn't want, because OEIS was our test set, but we should do that. I would agree that would be probably very interesting.
The resistance gets 75%. What it does is it generates Python program.
Yeah. So you can see that the number of inputs, so predicting the 10 next terms or predicting the first next term, so it's less, but it's very impressive that you only go from 33 to 20. You know, so once the model learns something, it's generally, it learns the sequence and everything becomes fine. Another thing that is interesting are the 2 last values. So those are the 2 functions that exist in Mathematica for predicting recurrences. So we're claiming here that we are sort of much better than the state of the art, well, at least as far as computer science, computer algebra are concerned. Okay.
Why would you say that the numeric model performs well for the space?
So it performs well because the numeric case has less inductive bias. So in the numeric case, you make no hypothesis on the kind of sequence you're going to see at training.
You are training the same sequences. You are training the same sequences.
No, I'm training. I've been training on the same sequences, but predicting the next number is probably gives you a little more, you know, space, I think. That would be the reason, I would think. Yeah.
A couple of questions. One, did you train a custom tokenizer, like so that the operations for definitely tokens or like the way the numbers work, I guess you could use spaces between.
Yeah, no, the tokenizer is totally standard. Basically, for the functions, you got all the operators, and there's
All
no
operators are their own tokens.
yes, yeah. And for numbers, it's just digits
Just by digit. Great.
in base 1,000 or 10,000.
And you can push that by spaces.
Yeah.
And then, how much for the data was it pre-trained on only the pairs, I guess?
There's absolutely no pre-training. The model is, everything is trained from scratch.
But just on the pairs.
Yeah.
And how much data?
I think we generated like between 10 and 20 million examples here. So you need to run through them many times, but it's usually it's the order between 5 million examples is usually a little not enough, and 40 million tokens 40 million examples you're very comfortable.
But that's, I guess, small compared to like language.
Yeah, but it's also not the same task. Language,
Yeah.
the models are huge. We have 50 million, maybe 100 million parameters here. So nothing to do with the billion parameters the others have.
Mhm.
And we're training on only one task, whereas they are by definition extremely multitask. So it's not, and they're unsupervised, which use a lot more tokens than when it's supervised. So yes, we did try. So you need a minimal size of the model. Here you needed 8, basically you need 8 layers and either 512 or 1024 dimensions. We tried larger models and you get very little after a certain size. Practically the complication that arises from the size of the model and the size of the number of attention head that grows, etc., sort of compensate the gain you have in model capacity. So usually you have a certain size, and scaling up doesn't help. Okay, a few examples of the kind of sequence the model could learn perfectly, no EIS. So you see it's pretty much anything. Fun facts. So the model, the language used by the model, you spoke about the tokenizer. The model only has so when building functions, all the functions are built with operators and with integers. So the predicted model don't know anything about floating point numbers or real numbers. But we found a way to use this model so that it would predict, a sequence representing a real number. So basically that's more or less a sequence, a linear sequence or a geometric sequence. And so you can ask the model to predict 0.333, and the model will find a way to represent it in its language and will correctly answer it's 1/3. If you truncate the value, it's going to tell you, oh, it's a little less than 1/3. So 1 on 3 plus a small number, which it will represent as exponential -6. If you give it pi with enough decimals, pi is in the vocabulary, so it knows it. It's a symbol. If you give it a little less than pi, it's going to give you this, and this makes perfect mathematical sense because our tangent of plus infinity is pi divided by 2. So a little less than pi is twice the tangent of a large number. Totally makes sense. Another thing is that if you look at the real, model that calculates the real values, we didn't have the hyperbolic trigonometry in the language, so the model didn't know it. But we could provide the model with, the values of hyperbolic trig functions, and the model will find this, which are the correct values. So it would build the correct representation. Even more interestingly, we provided it with values of the Bessel function, which are not representable, but it found us the correct first order approximation. Actually, by sort of looking deep into the beam search, into the many predictions the model can make, I could even find the Stirling formula by presenting the model with a factorial. So it's interesting. I'm not saying that all this is learned, but it shows that the model still learns something that is slightly mathematical, or at least would appear to us as slightly mathematical. Last point on this. So I said in the beginning, you remember the numbers are just the tokens representing 0, 1, 2, 3, 4, 5 are just conventions. They're just tokens that the model learns. But the model during training learns an embedding for those tokens. So it learns a way to represent them in high dimension. So if you do a PCA, actually that's a testing, so it's a cousin of the PCA. If you project those in low dimension and map them, you can see how the model represents the integers. And you can see the numbers from 0 to 10 are here. Model, then you have increasing values that are in the same place. So the model learns some kind of ordering. There are a few fun things. You can see the square, 25, 49, 64, 81, 100, 121, which seem to be at the outliers. I don't know what this means and no one knows, but it suggests that something is being learned. These are the exponents of the floating points. So I don't understand anything about the zigzags, but I can't help but notice the symmetry, which correspond to the mapping x on 1 on x. So, which is one of the basic operations that we saw everywhere in the thing. So the model sort of learned a couple of mathematical things because it had to in order to achieve the task. Okay. So that was my first example. But I'd like to show an example applied to science, so to theoretical physics. So this is current work with Lance Dixon from SNAG, Kyle Kramer from New Medicine, and Matthias Warren from the Niels Bohr Institute. For more people. I'm not going into the detail. I'm no physicist. Practically, we wanted to, so they are interested in predicting the gluon scattering amplitude. So scattering amplitude is the complex function that tells you when particles collide, what are the probabilities of the outcomes. Okay, and gluons are small particles, and this is very important because if you want to do experiments on the Large Hadron Collider in CERN, you need to calculate the probabilities of those collisions with very high precision. This is what the scattering amplitude is. The way you do it is normally you integrate over Feynman integrals of increasing loop orders. The loop is the number of virtual particles created and destroyed during the interaction. And it's a terrible mathematical problem. You get polylogarithm integration of transcendental function everywhere. And the best known techniques we have for the standard model compute up to loop 3. And this is totally insufficient to carry out the experiments that the CERN wants to do. So the people in Stanford came up with an idea which is called amplitude bootstrap, which says since the polylogarithm have a lot of mathematical property, let's exploit this property to guess the values of the integrals without having to complete everything. So this works in a cousin of the standard model, which is a planar and possible supersymmetric linear theory. And in this, they could compute one interaction, which is called a free gluon form factor, to 8 loops, which is incredible precision. So the way they do it, or the way it works, and now we're back into math, is that each loop, each approximation is represented as a symbol, which you can think of as a homogeneous polynomial of degree 2L, twice the loop, in 6 variable, A, B, C, D, E, F, non-commutative, with integer coefficient, most of them 0. So you see loop 1, so you have homogeneous polynomial of degree 2L, so -1 BD, -1 CE, -1 AF, these are the 6 terms. As you go up the loops, you got more and more non-zero terms, and at loop 8, you got 1.7 billion different non-zero terms. How is this computed? Well, that's lots of work and lots of PhDs, I think. Basically, you take all the symmetries and all the physical properties and you turn this into a gigantic integer programming problem that you send to people and MATLAB and all that. So you end up solving integer equations in tens of thousands of variables. It's very difficult and slow. But it's known that there are lots of regularities. So the idea is, could we use a transformer to speed this up and accelerate the calculation? So the first thing is, I said you have the loops, you have the coefficients, you have terms, long sequence and coefficients. Most of the coefficients are zeros. Can we tell whether a coefficient is going to be 0 or non-zero? So I'm giving it, a sequence of letters, A, B, C, D, E, F. And this one is 0, this one is not 0. Can I train a transformer to do that? So the idea is that if I build a 50-50 training samples of 0, non-zero, I keep a couple of terms, just for testing that the model will not have seen at training, and I train my model to predict, zeros and 1. Does it work? And actually, it worked very well. If you do that on loop 5, you train on 300,000 examples. That's about 60% of the symbol. And you can predict, the 10,000 reserved test sets, test examples that weren't seen. You can predict all of them except 4. So yes, you can. Loop 6, you can do it. You only need 6% of the symbol to predict the rest. So the model, we don't know what it does, but the model is able to calculate the zeros, which saves a lot of time. The input is the sequence, and the output is 0 or 1. And the sequence, you have 6 letters, so it's very simple. It's already, really in sentence form. So the next step is, okay, could you predict the non-zeros? Now that you know the zeros, the hard thing is the non-zeros. So you have keys, sequence of 12 letters, and you want to predict coefficients, which are integers in base 1000, so that the sequence are short. And for loop 5, if you train on 164,000 examples, that's 60% of the symbol, you can test on the rest, and you predict 99.9% of the symbol. So yes, you can predict. Loop 6 is even more interesting. You train on 1 million example, that's 20%. You get 98% accuracy. So you don't do everything, but you simplify the problem a lot. But you get those kind of learning curves. And if you've done deep learning, you probably haven't seen so many of those curves with two humps. So the curve learns up to 50%, and it saturates, and then it goes up. And the different curves here are different, either initialization of the model or different size, changes of hyperparameters. But you always get that two-step curve. What? The distribution of the integers. They're sort of Gaussian with fairly fat tails. Well, there are a few extreme values, and they're symmetrical around 0. So it depends on the loop. So I think for loop 6, the largest thing you'll see will be a couple of millions. And many coefficients will be between 1,000 minus 1,000 and 1,000. And the fun thing is that if you look, at what the model predicts, you have this curve, but actually you're predicting integers. And when you predict an integers, you're supposed to predict an absolute value and a sign. And we notice that the absolute value is learned very easily. But the sign takes a long time. Actually, you need to finish learning all the absolute values before the model starts learning the sign. And of course, personally, I was shocked because only 2 sign and so many absolute values. It shouldn't be that way. And we came back to the physicists who observed that, yeah, they had been struggling with the sign for a long time, and there's clearly a law, but they don't know it. But the hope here is to say maybe this, this performance tells you something about the underlying process. So it tells you something about the polylogarithm, tells you something about the Young-Mills supersymmetric. So yeah, there are lots of relations because you can calculate everything.
It's just like the definition of something like that.
So there's a big redundancy, which is the diagonal symmetries. No. You have small relations, and you have a lot of very long relations, which is why the solving gets very difficult. So the takeaway is that you could use transformer to complete the partially calculated loops. And this is interesting because this is a current, standing research problem in physics. You can learn coefficient with a high accuracy, which is, if you do so, you won't calculate all the coefficient, but you will calculate enough to simplify the problem a lot, and you'll use the relation to do that. And you get on the way an intuitive observation. That is, learning the sign, for instance, is very difficult. So the hope is that we could, maybe learn new physics with that, or provide new intuition that help learning new physics rather. So the next idea we had there is saying, okay, now we are at one loop, we want to predict the next one. How can we do that? So you remember a loop is a sequence of 2 L letters plus a coefficient. So if I want to predict loop L from loop L minus 1, there's one easy way. I take the key for loop L and I strike out 2 letters, and then I got a loop L minus 1 coefficient. And there are 2L minus 1 on 2 ways to do that. So suppose I provide the 2L minus 1 on 2 coefficients of the previous loop. Can I predict the next loop with that? You can think of it as the Pascal triangle. When you calculate, you can compute the binomial of order n by summing the binomial of order n minus 1. This is exactly the same thing, except you have many more variables and everything's non-commutative, so it's more complicated, but the same idea. So the idea is that you could train a transformer to do that. So loop 6 from loop 5, you have 66 integers, which are the parents. You provide the 66 integer, and you try to do the next one. And if you do that, you end up at 98% accuracy. So yes, it's possible. There's a function that does that. We don't know it. And unfortunately, it's very difficult to open the transformer and see it. But we have that proof of concept that this function exists. So one thing, whereas we don't know the function, we can try to see, we can try to know some of its properties by going with the same kind of experiment. So for instance, I'm using 66 parents because there are 66 ways to strike out 2 letters in my 2 algorithms. But I could use less parents by saying, okay, I only strike letters that are close by, 1 distant, 2 distant, 3 distant. So if I only strike adjacent letters, I only have 11 parents. If I strike adjacent or 1 away, I've had 21 parents. And if I train my model on that, you can see that for one away you lose, but for 2 letters, it's fine. You get the exact same performance, which says that the function I'm looking for doesn't really have 66 variables. It only has 21 if I choose them correctly. We push that further by shuffling the parents. You got the 66 parents or the 21 parents, and they're in some order, lexicographic order of the strikeout, well, some fixed order. Suppose that every time you provide a new example, you shuffle the thing. So you're mixing the values. Does this destabilize the transformer? It doesn't. Well, you go down from 98 to 95, but mostly not. So what I'm saying is that the function I'm looking for is sort of more or less invariant by a permutation of its variable, which is interesting. You can also see here that if you only provide the sign, 0, -1, and 1, you will predict the sign perfectly, but you're going to lose a little on the magnitude. If you only provide the magnitudes, you forget the signs. The magnitudes will be good, but the sign will be a problem, which sort of confirm one thing we've seen before.
And just to be clear, even if it's off,
Oh yeah, it needs to be the exact same. There's no mean square error. The reason is that the problem is a problem in integer, and we are not able to define a figure of merit of saying 1 off, or if the sign is wrong, is it worse than if it's 1 off? We don't know. So that's where we are now. So the idea is, okay, the goal would be to build loop 9, that would be a lot of fun. But more importantly, we're beginning to think that this is the kind of thing where we could probably help physicists by discovering or suggesting properties that seem to appear, which are difficult to spot because we're not used, to looking at those data. But transformers works in high dimensions, so there are things that do better than us. And if we can find those regularities, maybe we can help the physicist. So that's one subject. So that was the beginning of my talk. The second part is about the other way around, math for transformers. So how can you use mathematics or leverage mathematics to better understand what neural nets do? So to start, I'd say there are a couple of lingering questions for AI and transformers. The first question, personally, I always get is, do they really learn math? Or are they just exploiting shortcuts, parroting, as a famous paper says, statistical papers? Also, sometimes they fail. Are the failure predictable? Are they principled? Or does the model hallucinate, confabulate, as it's very often said? Second, can we explain the prediction? We saw all the problem with that in physics, or are the machine basically black boxes? And finally, a question which is specific to this. I generate my training data. What's the impact of the generator? How important is the way I generate the data on what my model can do or not do? So I'd like to present examples from 2 papers. The first one, linear algebra with transformer, 2 years ago, was a paper where I'm trying to see if the number could compute. So far, most of the work was on symbolic math. I wanted to see, could you do numerical math with that? So basically, short story, yes, if you provide the machine with matrices, represented as sine mantissa exponent with a certain precision, transposing, adding, multiplying matrices is easy. You train the model and it works. Interestingly, you can also learn advanced tasks like eigenvalues. You can also learn eigendecomposition. You can learn matrix inversion for relatively small matrices, but not 2, or 3, larger matrices. So it works. But I'm interested here. So the measure here is that I use L1 norm on all the matrices. So yeah, and up to I put a percentage of error, so like 10% or 5% or 2%. The result here are 5%. So it means that on average, the L1 norm of the matrix is 5% away from the L1 norm of the matrix I wanted. Yes, the sum of the absolute values of all the entries in the matrix. So I'm interested in here in trying to explain, you see if my matrix, if my math are learned. So I'm interested here in the eigenvalue eigenvector, eigendecomposition problem, learning to the eigenvalues. So in this problem, I'm giving the model a symmetric matrix M, encoded as a sequence, and I task the model to find a vector and a matrix H, verifying this. And the model will only see triplets, M, DH, so it starts to predict DH from M, but only sees example. But we know better. We've learned math and we know the spectral theorem, and we know that the D's are the eigenvalues, and so they're unique up to permutation, solve them and they're unique. And here we always solve them, so we learn them sort it. And H is orthogonal unitary, which means its rows and columns are orthogonal 2 by 2 and have unit norms. So the question is, do you think the model is going to learn these properties? And what does it mean? Would the model learn the properties? And so the way to test this is that you're going to train a model to high accuracy, but not 100%. You cannot learn from success. You always learn from failure in this case. So you need to train a model to 92% accuracy, and you test it on a large sample of 100,000 matrices, random matrices not seen at training. You end up with 92,000 correct prediction, good for you, and 8,000 errors, which are what I'm interested in, because I'm going to look at the errors. If you look at the test set, so I look at the 100,000, but including the errors, in all test sets, but 6, the eigenvalues are predicted with less than 1% error. Even when the model is wrong, the eigenvalues are correct. And in 99% of the test sets, all the rows and columns have unit norms, which means that I'm stating that the problems are the properties are learned. It's like a student that would get wrong a lot of problems, but there are a couple of things they always do right. These are learned. This is the same here. Some math have been learned, and the way I state it or the way I test it is because those properties are respected even when the model fails. It's even better than that. If you,
When it fails, is there a pattern, for example, multiple eigenvalues?
So multiple eigenvalues seldom happen. No, the one thing I've noticed when it fails is that the matrix, I don't have a good characterization. I can characterize it by the condition factor of H of the orthogonal matrix, which is a little larger than. What I noticed is that it's really the orthogonal matrix that is not quite orthogonal. It's a bit skewed like this. So you got, everything is almost orthogonal, but not quite. Yeah, but they're almost orthogonal 2 by 2, but there's a small difference, and it seems to be, so you have ranges of that, but I couldn't find a more precise characterization than that, at least. So the funny thing is that if you train the model, so you could think that maybe the model is learning you to do everything, and then at the end it learns the theory, like a cherry on the cake. It's not the case. It's not the case. If you train it for less time, the model achieves 70% accuracy, which is good, but not that good. But still, the eigenvalues are correct. The rows and columns have unit norms. So this seems to be learned early in training. I'm not stating that it's because it learns the properties that it used them to calculate. I don't know that, but at least it's learned early. Same if I go on 6-6 matrices. I was on 5-5 matrices. I go on larger matrices. My model is too small. I would need a larger model to train. The best I can achieve is 43%. It's not bad. It's not as good. Still, my eigenvalues and my rows and columns have the property. So I'm saying that these are learned early. It happens at the same time. It happens during training and early. The fun result here is that there's no hallucination. You've heard about hallucination in a language model, and this does exist. But in math, in supervised training, this doesn't happen. The model, when it's wrong, is roughly right, if you want. It's, the eigenvalues are correct. It's only the norm.
Two questions.
Yeah.
So you're still encoding things in like base 1,000. but-
Yeah.
And then you use the same embedding thing for everything else.
Yes.
Okay.
Yes.
And then the other question is, did you look at the difference on depth? So we know it's out.
So yes, I did. So the thing is that you need a certain depth in order to achieve that. More specifically, in those problems, you need a certain depth in the encoder. You can have a very shallow decoder, but you need a big encoder to process the input. And then the size of the encoder, you have a minimal size. And when you pass that size, everything works and there's no improvement from depth. The only gain you get when you have a much deeper model is that you can scale to larger values. So for instance, the 6x matrices couldn't be done with I think I had 6 layers. If I had 10 layers, it would work. So yeah. So what's interesting is that I end up having a single cause of failure for my problem. And it's a very, it's a failure that makes good mathematical sense. Practically, the model was tasked to find eigenvalues, and we know it's an easier task. We got the power law, we got, it's an easier algorithm to implement, and it worked. The unit norms were done, but the orthogonalization, the Gram-Schmidt part, if you like, was more difficult and it failed. So we can explain everything correctly. We could build, I said I could design a rule that predicts the model errors and success just by looking at the condition factor of the orthogonal matrix, which is logical. It has to be 1 for the matrix to be orthogonal, but it's possible to do that. I could reproduce this in the case of matrix inversion and show that in matrix inversion, the model fails systematically when the matrix is badly conditioned, which, would happen for humans, happen for NumPy, happen for everyone. So it fails for a good mathematical reason. So another thing I wanted to do with my linear algebra is just computing the eigenvalue problem. So I'm training all my model on symmetric matrices with independent coefficients. And we know that those matrices are Wigner matrices, and they have a very strong constraint in the distribution of their eigenvalue. Eigenvalue is distributed as a semicircle, symmetric around 0. So when I say I'm learning the eigenvalues of matrices, am I learning the eigenvalues of all matrices or just Wigner matrices? So in order to test that, I try to generate different training and test sets. So the columns are the test sets and the lines are the training sets. And so first line, first column is the semicircle, so it's a Wigner matrices. And then you got matrices with eigenvalue distributed symmetrically, got positive and negative eigenvalues, and you got also 3 classes of positive definite matrices, including the Marchenko-Pasteur, which is an approximation of statistical correlation. And it's interesting because if you look at the first line, you can see that, if you train on Wigner, test on Wigner, 100%. If you train on different matrices with symmetric eigenvalues, you go down to 30%, so not that good. And if you try to train on positive definite matrices, it fails. Samely, if you train from positive definite matrices and test on Wigner matrices, it totally fails. Okay? But the funny things are those 2 distributions, the Gaussian and Laplace. So the Gaussian and Laplace distribution, those are matrices which have been built so that their eigenvalues follow a Gaussian or Laplace law. So they are symmetric eigenvalues. Most of them are not, well, almost none of them are positive definites. But you can see if you train on those data, you generalize to Wigner matrices and even to positive definite matrices. So there seem to be training classes of matrices which are not natural. I never heard of those ensemble of matrices, but it seems that there are classes of matrices, if you train there, that seem to be more robust, generalize better than the rest. And it's only 1 point, but it's interesting because I've never heard of such results before. Another interesting thing is that suppose you use the distribution and train on larger matrices. So I'm training on eight matrices, and I only use 36 million examples here. And on 36 million, if I train on Wigner, I cannot generalize, I cannot learn Wigner. I don't have enough examples. But my Gaussian and Laplaces learn Wigner and learn everything. I'm saying that not only are they more robust, but they also train faster. So there seem to be kind of magical distribution that are, difficult to find. I was very lucky there. I don't know how to identify them, but on which, training works better, no matter the test that you use. Okay, so the idea is that here the underlying mathematics are sometimes learned. You need to investigate failures to do that, but you can, see cases where model learns. And there seem to exist special robust distributions that work better. So quickly, I'm going to present last results, which are last month, about learning the GCD, so greatest common divisors. I talked about it in the beginning. So the original idea is that I try to train a model to compare fraction. You give it 4 numbers, A, B, C, D, and you want the model to say whether A on B is larger or smaller than C on B. And this works. You need a few 100,000 examples and the model gets 100% accuracy, no problem. Now you do the same and try to get the model to predict the sum of 2 fractions, or just simplify one. And it totally fails. You cannot train it, even very large models. I went to 1 billion parameters, I can't do anything. So, when you see this, you say, okay, here you have GCD, here you don't. So maybe it's just a problem of, not learning the GCD. So, the drill now, you generate random pairs of integers between 1 and 1 million. Why 1 million? Because you've got a problem space of 10 to the 12, so no chance the model will ever memorize everything. You compute the GCD, train the model to predict, and test on a very large held-out data set. So if you start doing this, and you encode the numbers, the integers in base 30. So why base 30? You want a large base so that the sequence are short. It's easier. And you want, well, I thought that the composite base would help because, there are more divisibility rules. So it's usually easy to calculate fraction in composite bases. I'm using ridiculously small transformer, 1 layer, 64 dimensions, that's 300,000 parameters. That's about 1 million times less than large language models. So that's really the smallest you can think of. And you adopt at 95% accuracy after enough epochs. Okay, so this looks good. 95% accuracy means that if you take random GCD, random pairs of GCD, you correct 95% of the time. Exactly correct. Problem is that if you do the same in base 31, then it doesn't learn. So whether the base is composite or not seems to play a role. And actually, if you go on, okay. Yeah, sorry. If you go on and 10, you got 30, 6, 10, 2, 3, 31. So the result is different depending on the encoding of the base. And this is strange, GCD should not depend on how you encode the number. It's a property of the integers. So in order to understand what happens, you can look at the model prediction. So you got the model prediction for base 2, base 10. Let's look at base 2. So for each of those lines, you got the value. So I took all the elements that are GCD1 in my test set. That's this line. And I looked at the most common model prediction and its frequency. You can see that the frequency are always very close to 100%, which means when you have 2 pairs, AB and CD, that have the same GCD, the model predicts the same value. It's like if the model is able to tell that 2 pairs have the same GCD, which is fun. We humans couldn't do that easily, but it seems to work. The bold are the correct predictions, and those are 1, 2, 4, 8, 16, 32. Yeah, rings a bell. The model can predict the powers of 2. But it's even more interesting. Look at the odd numbers. They're always predicted as 1. And the even numbers, 6 is predicted as 2, 10 as 2, but 12 as 4. It's predicted as the largest power of 2 that divides the number. And this is systematic. You get something similar, with more divisors, but for base 10, this happens all the time. In fact, I could present all the predictions of my models in 3 rules. There's the first rule, which is prediction are deterministic. If you have pairs with GCD4, there's a unique value f of k that is predicted. The model always predicts the same value for all values. Sometimes f of k equals k, not always. Then the correct predictions are always the products of primes dividing the base. And the largest, the prediction made by the model for all of the values, it's the largest correct prediction that divides k. If you think of it, it's a bit like a seed. You got the values and you take the largest value that works there. Okay? And what does the model do? Well, what I suspect it does, or at least it's a rule that explains everything, is that it just counts the rightmost zeros in the case of base 2. You know, you got 28 and 14. This is base 2. You got 2 zeros, you got 1 zeros. The model makes them in and say, okay, it's 2. Okay, it's wrong. It should be 14, but that's the prediction it does. Sometimes it works. 1656 works perfectly with this. So it's a model that works sometimes and that achieves you a certain accuracy. It's probably what the model does. But still, the results are not very good. Am I predicting the GCD? Well, it depends on the base. The best I could do was 420. Yeah, 4 times 3 times 5 times 7. It's very engineered for it. And you end up with 97 random GCD predicted, because most GCDs, random GCD are small, but it's only 38 of the first 100 GCD correctly predicted. So not that good. So could you do better? Yes, you can do better if you have a larger base. So I looked at base 2023, which happens to be 7 times 17 to the square. And you get those train loss and those accuracy loss. And again, probably you've never seen losses like that. That's not really untypical from deep learning. So after 10 epochs, you know, it's as before. I've learned 1, 7, and 70, the dividers of the base. Divisors of the base. This is normal. Then nothing happens for 100 epochs. The lengths depend on the seed. There are 3 curves with 3 different initialization seeds. So it's sort of, there's some randomness there. But after a while, the model suddenly learns 3 and the multiples, 3, 23, 51. So it has learned divisibility by 3, which in base 2023 is not obvious. You know, there's no obvious rule. It's learned. Wait 100 more epoch and you learn 2 and 6 and 14, all the doubles of the previous one. And then you learn 4, etc. And you can account for all, and this happens for all large bases. Right? So you get, you know, again, 3 rules, deterministic rules that work all the time. And you can learn that for many different things. So could we do better? Yeah.
You only learn numbers lower than the base, smaller than the base.
So I seem to learn the primes in order. So only the primes and powers of primes, because all the multiples are learned in between, that's a C. But I seem to learn them in order. So I never seen, you know, and it always happened in large bases. So I never could wait long enough to, yeah, some of those have, it takes a long time, you know, some of those experiments run for a month. So it's really a slow process. So could you do better? And actually, yes, you remember my things with the training distribution, the magical training distribution. So when you look at the distribution we use here, you remember I'm learning from operands, which are uniformly sampled between 1 and 1,000,000. And the problem is that it means that if I do so, 90% of the numbers the model will see are over 100,000. And small GCD like GCD 6.9 will never be seen. And this is not how we were taught GCD. This is not how we teach GCD. We like, you know, people to learn easy case, sometimes even won't learn them, and then generalize. So there was a method for that, which is called curriculum learning. But the curriculum learning has drawbacks. You basically, curriculum learning, you start with the easy example and you increase the difficulty. But the problem is that the model tends to forget what it learns as it learns the next example. So it sort of doesn't work. But we could do something else. We could do log uniform operands. So practically, you sample so that K appears with probability 1 on K. Okay, so you sample from a log distribution. Then you will have as many 1-digit numbers as 6-digit numbers. So you're telling the model, here are these easy examples, please memorize. And the model is going to memorize these examples and learn the other, or at least at the back. There's no impact on the outcome defined, no big impact, and no impact on the test set. The test set are always the same. You get much noisier curves, but you can see the number of GCD learned. My best was 38, now I'm at 70. So engineering my training distribution improves everything. We can even do better. You know, I have the distribution of operands, but I also have the distribution of outcomes of GCD. And the GCD naturally are proportional to the inverse of the square of the number. So there are 4 times more GCD2 than GCD1 than GCD2, 100 more times GCD1 than GCD100, which means that when the model has to learn large primes, it sees very few examples. So it gets more and more and more difficult. So since I'm on log uniform operands, let's do log uniform outcomes. Oh, sorry, I'm still on the long uniform outcomes. So if I do log uniform, then I can learn up to 90 GCDs out of the first 100. So I can pretty much learn everything this way. You see? And the model learns prime after prime. So at the end, in the best model I have here, all the primes are learned up to 53. And they're roughly learned in order, sometimes 3 before 2, sometimes 2 before 3, but it's not 11 before 2 or 13 before 7. Right? So this is pretty much the best you can do with these models. So at this point, you might have a question. You might say, well, you know, you could balance. Could we balance more? Could we make the outcome distribution uniform? Looks like a better idea. And actually, that was, I still don't quite understand, but the surprising thing is that it doesn't really work. If you do so, the loss becomes flat. You still learn, you know, in arts, but your accuracy varies somewhat randomly from epoch to epoch. What happens in this case is that the model does exactly the same as before. You fix on one value, etc., and it classifies model in groups. You know, 1, 3, or the odd numbers of before, or the multiples of 2, or the multiples of 4 or 5. It makes classes. It partitions all the GCD into classes, but it has, you know, without with a uniform distribution, it has no way to predict the smallest value. It just randomly predicts a different number there every epoch. And so you're sort of losing the determinism. Part of the determinism is predicated on the fact that the distribution of GCD has more ones than twos than three, etc. And you have to keep that. This is what helped the model learn, you know, learning GCD in order, learning primes in order, and predicting the smallest value. Okay, so the takeaways from this is that finally, and this was a surprise, you know, in this, we say models are black boxes, and people try to open the model and understand the weight. I didn't even look at the weight. Just by looking at the prediction on a very special problem that has been engineered for that, you can understand exactly what the model does, and the model is very deterministic. You can also understand the algorithm. Basically, it's kind of a sieving algorithm, so it's primed, if you like, on the divisors of the base, and then it learns the primes in order and all the multiples of those primes. Classifies input pairs into clusters with common divisors and predict the smallest common divisor in the prime. Eventually, it will learn the GCD. It's a correct algorithm. You know, if you go high enough, the GCD will learn for all values. But it's interesting that it has nothing to do with Euclid's, which is the algorithm we would recommend. It's a much less efficient algorithm than Euclid, because it's, you know, Euclid will be log, well, depending on log, here you're going to need to learn everything. But still, a correct algorithm is learned just from examples. And the last point, which is, you know, it's my second point on that, research will go on, is that training distribution really matters. And you can really change everything by finding the correct training. The log uniform distribution of integers, I'm pretty sure that would be useful for large language model doing arithmetic. I mean, there's no reason why it would work for GCD and not for addition and multiplication. So the main conclusion is that you can learn quite a few mathematics, quite a bit of mathematics with transformers, and it's sort of a new field of research, and I'm sure it has application in science. But also the other way around, that mathematical tasks are a perfect benchmark to try to understand deep learning. Because, you know, when your language model fails, the only thing you can say that it fails. When it's mathematics, you can engineer the training set, you can engineer the test set, you can choose the problem so that it answers a couple of questions, and you can leverage all the theory. That's my side. Thank you very much. Yeah, sorry, I was a bit long.
No problem.
Of matrix analyzation, so you mentioned the typing language is easier to learn than the orthogonality. So there are any ways to test this from the level of statistics? If you want to define maybe the correlation between matrix and the orthogonality is stronger than the correlation between matrix and the orthogonality. Is there any ways to understand?
Okay, I wouldn't know enough mathematics to be able to have a definite idea on that. What I know is that there are simpler algorithms for calculating, especially the largest eigenvalues, than calculating the eigenvectors. So that would be, for me, the reason why the model probably has less difficulty. Yeah, I don't think I know enough linear algebra to be able to get a precise idea. I had a great suggestion one time when I presented that, which said instead of eigenvalues, you should try to get the model to predict the Hausfelder reduction, the reduction, because whereas the calculation of the eigenvalues is somehow transcendental, it's not. The other one is just shuffles, and it's relatively simple. So it would be interesting to see if there is a link between something that is obviously, much more complicated for us and much easier for us, at least from a intellectual perspective. And so I don't know. So far, the experiments I have show that sometimes the difficulty is the same for human and machines, and sometimes you have things that seem, for instance, in the dynamical systems, when predicting, we would tend to say that, the spectral mapping theorem is much easier. It's an easier result than the Kalman theory of control. And inside Kalman theory, predicting whether a system is controllable is much easier than predicting the control matrix. And we don't see that in experiments. Both things seem to be very much as easy or as difficult for the transformer. So yeah, but yeah, I don't know how you would need to think about, building tasks, building experiments that would be able to show what could be done with that. Yeah.
For some of these applications, you want to have some error bars, some confidence.
Yeah. Yeah.
Because getting up.
Yeah, I agree. So there are two ways to think of that. So one way, which I find interesting and promising, is that they don't hallucinate. So when they do something wrong, they do it not totally wrong. But as I said in the beginning, in order to do that, you need to have a verifier. You need to have an external tool that checks your model. So in the kind of scattering amplitude, it's pretty good, because what you don't predict, you put them aside. And you have, those linear relation to fill in the missing elements. So long you have a certain capacity, you could use it in science. But of course, you would never want to use those tools instead of deterministic algorithms. So it's not a replacement for, and it's very unlikely that they will be faster than algorithm. The way I see their use in science, at least in math or physics, is more that I suspect these tools could probably provide specialists with some intuitions, some different vision of the problem. And that might be, I don't know how to do that now, but that I would say this would be the better way to look at their use in science, rather than have that kind of magical black box that sometimes predicts a solution and sometimes is wrong, which is not a good idea. Yeah. Yeah, you would need that, definitely.
Was the prediction that it was deterministically wrong, because that suggests that you could train another model on the output and you'd get the right answer. Does that mean that you maybe should have had more layers, or?
So I tried to have, so on the very first experiments, I went very, very large in both directions. So I ended up with model with just, a few 100,000 parameters. And I had model with more than 1 billion parameters, and I couldn't spot any difference. So this seems to be very resistant to the model size. I think the reason of that is that, the rules they learn they're really shortcuts. If you think of it as a loss, minimizer and a loss, they're probably very deep valleys that are learned in the beginning. And once you're there, having more parameters won't get you out. Whether you could retrain the model and improve that, I think, yes, I think you could probably, you could always represent in multi-base, have kind of the same representation, have that in 2 tokens. You could have the 2 numbers represented in 6 different bases. And then have kind of a Chinese remainder argument, that says you learn the predictions everywhere, but
for the generic phenomenon. If the model is basically recognizing some phenomenon but giving consistently the wrong answer, so that there's just some decryption,
Oh, yeah, you could do that, but then you wouldn't get the right result because you see here. Yeah, you got one for every odd number. So when the model predicts one, the only thing you can say is that it's odd. No, unfortunately, it's not. So you couldn't save the model.
Possible frame the GCD on several bases at once, like first so many primes.
Yeah, that would be the idea. You could have represent all the values in base 2, base 3, base 5, base 7, and have them next to each other. I haven't tried. I think it would be possible. Yeah, I think it would happen.
There's a question in the chat. Would you like to look, or
Yep.
would you like me to read it?
Can you read it to me?
Okay, Gonzalo Sean. We know that general neural networks have back error propagation mechanism to correct errors. How to implement an error correction mechanism in the mathematical derivation of the transformer model? And how do we know that every step of the mathematical derivation of the transformer model is correct? Do you need someone to verify every step?
So you definitely need you need an external tool to verify steps. As for the error correction, there's a problem there. It's that if you have a continuous problem, then the backdrop error propagation will mostly work. So you could use that for matrices. You cannot use that for GCD. GCD is totally discrete. So the thing is that you learn by, gradient, etc. But you cannot, and sometimes the model implements a gradient descent as the algorithm. But in a very discrete problem, you cannot, implement correcting codes, or there's no easy way to implement them from uniquely a descent, gradient perspective. Depends on the model, I think is the short answer.
Thank you very much. A very stimulating talk. We'll continue our discussion in private. And we may have a talk on October 11th. We won't have a talk next week, but I'll announce it when we know. So long, everybody. Have a good week.